Hello everyone, my name is Viraj. In this video tutorial, I will be presenting input-output management by a operating system. Objective of this tutorial is to identify the role of operating system in handling computer input-output. Now, why we require the input-output management? There are two main jobs of an computer. One is to handle the peripheral, that is nothing but the input-output devices. Second is the processing the instruction set, data sets, and so on. Most of the time, input-output become the primary job of an computer system. For example, web browser or an text editor. When you have been handling a web browser, what you have actually been doing is communicating on to the Ethernet port or a Wi-Fi port, and computer is just a mere representing the data structure or the input-output of a corresponding entity, whereas the processing ability of an computer or a CPU is not utilized to the larger extent. So it is very important that computer system should manage the input-output devices and control the operations of input-output.
Okay, challenges faced by the operating systems are the variety of devices. Okay, as we could observe in a computer system, the devices or peripheral which have been connected of variety of type with the variety of the functions and variety of a data rate. Again, the specification port structures are been of different kind. Now, to assimilate this all stuff, there are many complexities that operating system has to face. Majorly, the devices have been categorized in two types. One is a block transfer, second is the character transfer device. Block transfer devices transfer the data to the computer system or to the main memory in a block of a data that might vary from 1 Mbps and to the hundreds, whereas the character transfer device might communicate with the computer in terms of bit or byte. So depending upon this variety of devices, the corresponding, so it is very difficult for the operating system to monitor and manage this kind of devices. Now next is an memory mapped I/O. In this case, the address of an memory field will be assigned to the dedicated I/O ports, so that there will be a communication between the input-output devices and a CPU. So that whenever the particular device has been requested by a process, a CPU will be knowing the exact address of the corresponding devices and will be able to fetch it. This is possible using a memory mapped I/O. Again, memory mapped I/O is having three different kinds of an address space. One is a two address space in which the main memory is been separated and I/O ports will be given a different memory unit and the address structure for the access by a CPU. Whereas in second case, we can observe that only one memory unit has been utilized, a part of which has been utilized as an main memory, whereas the rest part is, or some dedicated part of it, has been utilized as an addresses of a corresponding I/O field. The third case of this is known as an hybrid address space, in which the peripherals which have been essential have been kept in the one address space, whereas the peripherals which are the non-essentials or depends upon the application were been kept on to the different or separate I/O space or separate I/O ports. Now let's see their bus architecture. Now CPU will be able to communicate using a single bus architecture in the first example. Now the CPU is communicating with the same bus structure to the main memory as well as an IO. Now the difficulty with this, or the drawback of this, is that IOs, as we had seen earlier, that IO speeds are of variety of kind, and in most of the cases it is far less than the central processing unit. So while communicating with the IO devices or fetching the data from the IO ports, the instruction set from the main memory cannot be executed in this case. Now to avoid this and to keep the task of a CPU in a running phase in a second architecture, that is dual bus architecture, a larger bandwidth bus structure has been allocated from a CPU to the main memory, along with a regular bus structure for memory and IO. With this, CPU can continue to execution of a process while it has been communicating with the IO devices, so that a throughput of a CPU can be improved. Now the direct memory access, it is a very important concept whenever we are talking about the input output port. The expectation from the expensive general purpose processor is that it should process as much of instruction set as possible, not to wait for the status of an input output devices or work onto the input output devices. So we should give the priority on the execution of an instruction set. That's why we introduced a direct memory access. Now this will avoid the overburden of a CPU and will introduce a direct memory access. Now let's check how it will be having a dedicated chip controller for the data transfer and monitoring. So once the data is ready, then and then only a CPU will be given the acknowledgement that the data is ready and he can fetch the data or start executing for the corresponding IO devices. So let's check how DMA works. Now this is a diagram which explains the or illustrate how a CPU has been working alongside of an DMA. As you can see, we are using a single bus architecture for an example, and we are having a CPU, then main memory and the IO port. Now in this case we are considering a disk controller for an example for the IO ports, and along with this the new part or new controller has been introduced. It's called as an DMA controller. Now whenever the IO is required to be fetched, let's take an example that we need some data from the hard disk drive. Now CPU will give the DMA instruction that he will require a specific data from a hard disk drive, then the address field of that corresponding data, the count of how much byte or bit of a data has to be taken out, and the control unit of an corresponding entity. Now from here onward, DMA will take the control of a corresponding task until the data has been solely transferred from the hard disk drive to the main memory. Now DMA will give the request to transfer the data from the hard disk drive to the memory to a disk controller, that is nothing but a IO device. Then the data will be transmitted by the IO device from the hard disk drive to the disk buffer, from the disk buffer to the main memory. Once the data has been completely transferred, disk controller will give the acknowledgement to the DMA controller. Now as the data is ready for the execution, DMA will give this message to the CPU by means of an interrupt. So let's check now the layers of an input-output softwares. So first we see is an user level I/O software. It is nothing but the user interface in most of the cases which has been seen or observed by all of us. It might be a display unit, it might be a mouse pointer, it might be the output of an keyboard. Then below this we have that device independent operating system. This has a major role to handle and make a synchronize all the IOs. Below that is a device driver, followed by an interrupt handler, followed by the actual hardware of an corresponding input-output. Now let's check the interrupt handler. It saves the register. If an interrupt occurs, it saves the register which are not already been saved, make a copy of a corresponding context, then put it on a stack and proceed for the interrupt service routine. Acknowledge the interrupt controller and copy the register from where they were saved to the process table. Then run the interrupt service procedure, which is nothing but the IO procedure. Then after the completion of that, choose our next process to be run from the corresponding queue. Then set up the memory management unit and its context to process for the next process. Then load a new process register including its program status word and start running the new process. So with this, the IO has been completed its task, and then again it has been handed the control has been handed over to the existing process which are in a queue. Next is the device driver. Device driver present a uniform device access and interface to the IO subsystem, much as a system calls provide a standard interface between the application and the operating system. As you can see over here, we have a user program. Then user program interacts with the operating system. At operating system, through the operating system, we access the variety of a device driver, and those device driver enable us to handle the corresponding devices. Now the device independent IO software, nothing but an operating system. It plays a very major role in this kind of operation. Now its major task is to allocate and release the dedicated devices so that the corresponding devices will be available as and when they have been required or requested by a particular process. If the corresponding devices were abruptly been taken away from the system, then the error should be reported by the operating system. Also, the task of operating system is to provide a uniform interfacing to all the device drivers and their subsystem. Now for that, you could observe in this diagram that operating system in first case is enabling various multiple devices with the multiple socket type. Now due to this, the particular devices will fit in a particular socket only. Now there is no harm if we run with this kind of a system, but what if we have the more number of peripheral than just 3? Then we are not being able to interchange their socket, so we have to provide as many socket as the number of interface or number of IOs we have in the operating system. Contrary to this, in the second case, the operating system provide a uniform interface to all the device drivers and IO subsystem, due to which those can be replaced and their order can be varied as per the requirement, so that it look like very simple and plug and play for the particular device. Next is an buffering. Now, why we required a buffering? It's all because, as we all know, the CPU is working at much higher frequency corresponding to the IO devices. Now, in that case, can we keep the CPU waiting for the execution of a data which has been coming from very slow kind of a devices? No. To avoid this, the first buffering has been introduced. So the first reason is the data speed mismatch. Then second is the data transfer size mismatch. As we had seen, there are character devices, there are block transfer devices, so data transfer size mismatches very often in the computer peripheral system. Third is the use of buffering to support the copy of semantics for the application IO. Suppose some task has been generated by the IO which has to be executed by a CPU. So in this process, a CPU will take some time. After, a CPU will come back, the IO might request some another task to be performed by a CPU. Now, in this case, there won't be any communication and confirmation that which previous task has been performed by the operating system and whether it has been asked by the particular IO. For that, we can keep the copy of the previous instruction which has been generated by IO, which will support the semantics for the particular application. Now, let's check the diagram. In the first case, it does not a modem which is working at very low speed. In most of the case, it is working at kbps or in the rate of mbps, whereas the CPU has been working in the gigahertz speed. So in that case, a modem is directly generating the data and providing it to the user space. So user has to wait for every character that has been generated by the corresponding modem. Now, this isn't a good system. So what has been done, in a user space, some buffer has been allocated. Once that buffer is full, that will be displayed onto the screen for the user interaction. By that time, modem will be keep on filling the corresponding buffer. Now, with this, the drawback is that when the data has been displayed, by that time the modem is also generating the new data to be communicated. Now, where we can store it? So for that, again in the third system, you can see we have one more buffer introduced in a kernel space, another is in a user space as earlier. Now, due to this, whenever the kernel space has been filled, it will be transferred from kernel space to the user space, and then the modem will keep on filling the kernel space. This again has the drawback as seen in the earlier case, but with the lesser effect. Yet with the high speed IOs, this might be a drawback to the system. To avoid this, the dual memory have been introduced, or dual buffers have been introduced in a kernel space, which will allow modem to store the data in a first buffer. Once the first buffer is full, it can fill the corresponding data into the second buffer. But during that time, when the first buffer has been filled, it can be copied from the kernel space to the user space. So user does not have to wait, and modem also does not have to wait until the kernel space is empty. Buffering type. There are 4 buffering types of an IO devices. First one is no buffering. As we had seen earlier, it has a drawback that user has to wait until and unless the user buffer has been filled, and then it has been displayed onto the corresponding user profile or user process. Second is having a single buffer. which will allow the IO device to store data in a kernel space, and that will be copied into the user's process space. Third one is a double buffering. As we had seen earlier, we have two buffers. The IO devices will be generating the data and will be storing it in a one space. Once that corresponding space is full, then from that kernel space it will be moved into the user process. By that time, this will be shifted from the first user space to the second, and this will allow both to work in the same main memory or same kernel space at the same instance. In some of the cases where the IO devices are able to generate data in the larger amount, there a circular bufferings have been used. Instead of only two memories in a kernel space, multiple memories have been allocated in the circular buffering or kernel space, which will be simultaneously been executed from the IO devices, and that will be copied into the user space, so that none of them has to keep on waiting for the filling of a data or copying of a data from the corresponding space. These are the references for the today's video tutorial. Thank you.